Good morning, everyone. Welcome to my session. My name is Mikhail, and I'm going to speak today about the cloud infrastructure and cloud automation from the perspective of software developer. So, a bit on my background on this picture guy, the developer. I've been writing software for like 15, 20 years, and I didn't do much with cloud automation at least until 2, 3 years ago. Back then, I worked in a small team, DevOps team, where we were developing applications for the cloud, specifically for Microsoft Azure. Or worked with IT people to develop cloud infrastructure, and we tried to do everything right. We had CD pipelines, and we also discovered the approach called infrastructure as code, so that we could describe our cloud infrastructure as a bunch of JSON files for Azure ARM templates, and then every time we needed a new environment or every time we needed to update an environment, we could just go ahead and take these templates, send them to Azure, and magic would happen. Cloud resources would be provisioned and created for us repeatedly and reliably. That's all good. However, the experience of creating those ARM templates was quite painful. Just for one application, I remember we had like 5,000 lines of JSON, and writing those JSON lines were quite a difficult task because we had to go like online, Google something, copy paste large snippets, try to run them. It will say run for 5 minutes, then it will fail at some point. Have to figure out why it failed, change a little bit, try again, and so on and so forth. Writing applications that I was used to, the process was quite painful, editing all and creating those JSON files for infrastructure automation. So I thought there must be a better way to do this. Maybe we should apply some of the practices of software development work to infrastructure provision. And that's what my session is going to be about today. So quick intro, my name is Mikhail. I work as a software engineer at Pulumi. My cloud is biased towards Microsoft Azure and serverless platform as a service kind of services, but the presentation today is going to apply to any cloud and any service really. If you have any questions after my talk, you can always reach out to me on Twitter. You can see the handle below. Or if you go to my website, you will find other contact means like email or LinkedIn or whatnot. So let's get started. For today, again, my talk applies to any cloud, but I'm going to give examples from Azure and AWS at the same time. I'm going to start with more traditional infrastructure as code tools like CloudFormation or Terraform, give some advantages and disadvantages of those tools, and then I'll show you the tool that I'm working on, which is called Pulumi. If you have any questions, please go to slido.com and then use hashtag DevOps 2020. Put your question there, and in the end, I will try to answer them after the session. The whole two, by the way, if you should select there. So what's so special about cloud? Why is it great for automation? Well, cloud is the first thing ever for infrastructure which has API for everything. Every time you want to create a new resource, be it a virtual machine or a database or whatnot, there is an API endpoint, a REST API endpoint. In the case of Azure, it's called Azure Resource Manager, but other clouds also have them. And wait several seconds or several minutes, and then you will get the response back and you will get your resource up and running, which is sort of magic compared to the world of hardware and virtual machines. So it doesn't matter which client you use for your infrastructure provision, be it like web console or a CLI in your shell or some third-party product. In the end, they all call that API endpoints to create infrastructure. So the very low level that you could automate your cloud is actually making those REST calls manually, like fire up Postman or curl or whatnot, compose that HTTP request and send it to the endpoint, wait for a response, and get your cloud resource back. However, this is like assembler of automation. This is very low level. It's very hard to use, very laborious. So not a lot of people do actually this. So that every cloud and runtimes, Node.js, Java, .NET, Python, whatnot. So you can write code like this instead of writing HTTP requests. But in the end, when you compile and run it, it will translate to the same calls to HTTP endpoints of the cloud. The benefit here is that you get all the nice things of SDKs and your favorite language, like you can get IDE support, IntelliSense, so that's kind of thing. You get compile time errors, you make it, so the feedback loop is much faster than if HTTP requests. If you are more of an IT person, you are used to your CLI commands. Every cloud has CLI commands, AWS CLI, Azure CLI, and so on and so forth. So you can do the same. They all translate to the same HTTP calls in the end. However, this is still very low level in my opinion. First, you have to write it in imperative style. So if you have to create multiple resources, the steps you need to provision in order so that you get the desired application. So this is very imperative, and you're not describing what you want to get, but you're describing how you want to get there. Also, because environments exist for months and years, you end up writing a lot of upgrade scripts from state end to state end +2. And time you get a lot of these scripts, and they are relatively hard to manage over time. Also, if your script fails in the middle, usually it's hard to test them on these scenarios. So you will not actually know what the current status of your infrastructure is when it fails, whether you can run it again and it's idempotent and will just succeed, or will it create double resources, or will it fail because something already exists that it doesn't expect. So it's quite error prone and challenging. Therefore, there is a notion of desired state configuration, and the idea is that it is steps how to provision your infrastructure. You describe the desired state of the configuration. So if I paint it on a small chart, you describe the target configuration, and then doesn't matter what the current configuration of your infrastructure is. There is a tool that compares your target state with the current state, and then it figures out the difference and the exact steps to bring any current state to the target state of your infrastructure. So if you deploy for the first time, the current is empty and target is just created from scratch. If your current is equal to target, it will do nothing. But that's the goal of the tool, to figure out the difference and apply the difference so that they are reconciled. A useful way to look at this is to describe both states in terms of graphs of resources, where each node is a resource in the cloud, and then arrows between or edges in the graph are dependencies, because dependencies are very important to figure out the difference. So these tools have to be good in terms of graph description and graph manipulation. There is still quite a lot of challenges in desired state configuration tools. First, they have to be expressive enough so that the user or developer, you, could describe any state of your infrastructure. Also, it has to be good with managing dependencies between them and figure out the correct order to create or delete something to transition from any state to any other desired state. And because those two are never perfect, actually, it should also be transparent about what it's about to do. So let's say you described your infrastructure, but you also already have an environment. Before any changes happen, ideally you would see the exact plan that the tool figured out for you. And if something is wrong there, like it's trying to delete a database or whatnot, then you would stop it and make corrective actions. So every cloud vendor has their own tool for this, and they're all different. AWS CloudFormation, Azure Resource Manager, Cloud Deployment Manager, they all different tools from the vendors, but on a high level, they are sort of the same thing. It is a markup. So all of them are using either YAML or JSON or both to describe your desired state. This is an example of Azure ARM template, a JSON where you define resources. This one only has one, but you can define dozens of them. Then you send them to Azure, and Azure applies it to the configuration. This is an example of AWS CloudFormation. They started with JSON. These days they support YAML mostly, or at least most people use YAML, but it's still markup, still text file where you define your infrastructure. And you can already see that it gets in a little bit more complicated. There are references here, if statements there, so it becomes to be a language inside the. There are also third-party tools. The most known one is Terraform. And Terraform works for multiple clouds. That's its strong side. And it's actually still markup, but they invented their own configuration language, HoshiCorp configuration language, or HCL, which is a DLL to define cloud resources. And it's still text, but it's a bit more lightweight. It has special constructs to describe graphs of resources. So it's more productive and more concise, sort of. Still, in my opinion, markup authoring experience is not that great. When those tools are just get introduced, they are just JSON or YAML. So the tooling doesn't exist. The tool, like your ID, can only help you to create a valid JSON, but it doesn't help you to create valid ARM template or valid CloudFormation. So every vendor has to plugins for VS Code so that it would help you edit them and highlight errors if something goes wrong. But from day one, tooling doesn't exist or it's quite poor. And if you look at things like Terraform, the tooling is still not great up to today, even though the tool is about 5 years old. It's particularly challenging to write this scratch, so like sit down with empty IDE and write your template. Usually it's copy pasting from somewhere, adjusting to your need, and it's hard to discover all the options without going to the documentation or actually trying things out. And one particular problem is, of course, the size, because you still describe it on the lowest level possible. The size of those templates, as I alluded to my action, is still quite high. It can be easily hundreds and thousands lines of markup, which are quite hard to read and support over time. One example application that I wrote or found online is like a URL shortened tinyurl.com or aka.ms or whatnot, bit.ly, where I created serverless functions. They listen to an endpoint. If you go to that endpoint, it's the path of the URL, looks it up in the database, and if it's there, it redirects you to the different URL, a longer one. Very simple applications. I only need lines of JavaScript to implement it. But in order to provision all the resources in Azure or AWS, all the API gateways, permissions, and whatnot, I had to write about 200 lines of markup for those resources. So 20 lines of code, 200 lines of markup, order of magnitude difference. And I want to be focused on writing code and not writing markup. So this doesn't feel right to me. Also, as I already mentioned, those languages are not just YAML or JSON. They are languages to define dependencies, like in this example of ref attribute. They have conditionals these days. So if you apply special syntax to an attribute, it will evaluate it, and if it's false, it will not deploy the resource. Every language, every infrastructure is, because you want to deploy to multiple environments that are slightly different. Introduce things like loop. This is an example of Terraform, where there is a loop to go through files and then deploy bucket objects for every file. And you can see there are special constructs and they differ per language. Your reusability is quite hard. So if you want to deploy several resources and you end up copy pasting them usually, or doing some awkward things with linking templates one from the other. There is no way to create simple high level abstractions and also to package and distribute them for company, let's say multiple teams or in large open source community. Terraform sort of has modules which are still not there, but the right step in the right direction. The stability is quite hard. If you want to test your infrastructure, usually deploy it to cloud and then test it. You cannot really test in the infrastructure, or even deploy the part of your application and then only test that in integration. So when I look at these problems from the developer point of view, I think we solved them a long time ago for general purpose programming languages. We have all those great tools like IDEs and used to help us not make mistakes, and package managers to distribute things, and semantic versioning, and so on and so forth. So my presentation is, what if we apply all those tools that exist for many years, and that's what I work on in the open source project called Pulumi. for the rest of my presentation, I'm going to show you why it sort of makes sense programming languages for infrastructure definition. So Pulumi, again, is open source. You can use it for free. And it supports defining infrastructure for multiple clouds in currently 4 runtimes: Node.js, Python, Go, and .NET. In this presentation, I'm going to give examples in TypeScript just because I have to, but you can hopefully easily read it and translate it to your favorite language, let's say Python or Go if you do infrastructure stuff. Pulumi works for multiple clouds, so it works for AWS, Azure, GCP, but also things that are not necessarily cloud, like you can create Docker images or Kubernetes deployments, or even things like PostgreSQL, Oracle, or New Relic. So anything that's in there can be a provider, and they all, again, open source, so you can plug your own thing if you miss something. At the moment, we have like 40 providers. And finally, some code. So this is a basic Pulumi program where you create 2 Azure resources. One is a resource group, like a container for other resources, and the other one is a storage account to store the files. And you see that creating a resource or defining a resource is just calling a constructor of a class in TypeScript. So I call a constructor, I create a resource group, and then in the second assignment, I can use resource group.name, the property of resource group, to create a second resource. And just because I used the variable resource group in the account definition, Pulumi will be smart enough to figure out that dependency in the graph and deploy the resource group first, and then wait until it's done to start deploying the account. The most important here to understand is that this is still desired state configuration. So this is different from code that I showed before. When I run this program, no resources are automatically created. It just creates the definition of the graph of the resources, my desired state. And it doesn't matter which current state of my infrastructure exists. I still write the target state only in my program. So I don't write update scripts. I just write one program and evolve it over time. The resource that I need to deploy is the S3 bucket. You can see that I get all the IntelliSense and the tooltips about the properties. If I make a typo here, it will show me red squiggly. So it's very fast feedback, and I can easily write programs without running them and be sure that they are more or less correct. And then I can also do things that I would do in my other TypeScript program, like make loops here, for example, or use other libraries to list the files. So what I do here is that I request all the files in my root folder that's on my disk here. And then for every file in that folder, I extract its name. I understand what kind of MIME type it has. And then for every file in the loop, I create a bucket object. So this means that I will deploy all the files from a folder to S3 and make it a static website. And the final thing here is that I need to export the actual URL of that website when it's done. I don't know it in advance because it's going to be assigned by AWS. So I need to export a variable for my program called bucket endpoint. And then I construct it from the property bucket website endpoint. So in order to deploy this infrastructure, I actually need to jump to my terminal. And then I'm going to type a command called pulumi up. Pulumi is a CLI that I already installed. And I'm in the folder where my program is located. So I run this program, and it will evaluate my TypeScript file and show me the preview of resources that are about to be made. So in this case, you can see that it found 2 files about HTML and index.html, and it's about to create this resources in the cloud. This is just a preview. Nothing is done yet. If I'm happy with this preview, I can say yes. And then my program runs again. It gets created. It gets compiled again, gets run again. It gets the same graph definition, and those resources are actually deployed to AWS this time. And as a result, I get an output from my program, a bucket endpoint that I defined. And then hopefully, if I click this URL, yes, I can see that my files were deployed to AWS successfully, and I can see my website. So now, to make it a little bit more interesting, I can go back to the program and like change something. Say I change the file to like change the context of the file, company page, let's say. And then if I jump back to the terminal and run Pulumi again, it will run the same program. It already knows that last time it deployed all the resources, so it can compare the current state of the environment. All right, I didn't save something. So let's say I rename the file, yes, to company.html to deploy a different file. So I run the program again. It would compare the existing environment to my target definition. It will say, okay, I know you want to delete about HTML and create company HTML instead. Are you sure you want to do this? And if I say yes, then it will only apply the difference between the two states, the previous state and the new state. So this is still how desired state configuration works. Finally, when I'm happy with this, I can also say Pulumi destroy. If you ever worked with AWS, you know how painful it can be to delete all the resources that you created, say, manually while clicking in the console. Here, it's just it compares the empty target state with the desired state, with the current state, and then deletes all the resources one by one. And my environment is clear again. So back to slides. So for the rest of the presentation, I want to give a couple of more examples of like why this makes sense, why I think this is useful. First, let's talk about serverless functions, my favorite topic. In order to deploy Azure functions, a serverless function in Azure, I need to create 5 resources. So the function app, plan to run it, and some objects in the storage to contain my function code and also to help the function run. This is quite hard if I want to just run a hello world application in my Azure functions. So instead of, if I need to make this with ARM templates or something, it's going to be like 100 lines of markup to deploy this. Instead, I could create a component resource, that what we call it in Pulumi, that would abstract away those details for me and would expose just a basic API on the top level. Like, I want to deploy function app. I don't really care what other resources I needed to be deployed. I just deploy function app for me. Here is your binary. So we did that. The resource is called archive function app. You can see it on the second assignment. And what it does, it just takes a path to a folder on a disk, and then it will zip it up, upload it to a storage account, point the function app to that storage account, and wire everything together so that my application is deployed as needed, and I don't have to care about the details of how it works. And it just gives the endpoint back to me. So it's a higher level abstraction on top of low level resources that you can create in your code. And if I run this program, this simple program of 5 lines of code in Pulumi, you will see the tree of resources that are about to be created. So you can still see all the details that have to be provisioned, but you don't have to care about them every time you need to create a new function app. It's abstracted away from you. Another example, you can make this component as sophisticated as possible. You can make, for example, optional settings. My previous example deployed a Node.js function app. If I want to deploy, say, .NET instead, I pointed to a different folder on the disk, and then I changed the setting runtime to .NET. By default, it was Node.js, but if I pass it explicitly, then it would wire all the proper settings in function app so that it runs .NET Core instead of Node.js. A slightly more sophisticated example, if I need to deploy Python functions, I need to create a separate Linux plan. That's how Azure functions work. And then I define this plan as a separate resource. And then I have yet another extra option in my archive function app component called plan that you can pass my Linux plan to. And if this plan is passed explicitly, the archive function app will not create its own plan, but will use this one. Otherwise, it would create a new one. So you can make your component as flexible as possible. You can imagine there are a lot of if statements there, checks, maybe some for loops, but the public facing contract is still very simple. It's just a bunch of properties that you assign to it. And that's the goal of designing a component, a reusable component, so that the life of your end user is as simple as possible. And then you can share these libraries with your colleagues or with broad community. Another neat feature, because we are just running inside a general purpose programming language, we can also combine the code of the function with infrastructure definition. So what this snippet of code does, it actually creates the complete function app in Azure with the code that I provided to callback. And every time a URL, HTTP URL is triggered, this code will run. And Pulumi does all the smart fun stuff to zip it up, to put this code into the Azure storage container and so on and so forth. And you'd only care about writing this small snippet so that it runs in the cloud. You can also do this for things like queues. So you define a queue in your storage account, you put it in the same program, Pulumi program, and then you sort of do it like you would do in Node programs. You say queue.onEvent and then pass a callback, and this callback will be called every time there is a new queue message. So this opens up some doors to like mixing infrastructure and application code. More examples. Let's talk about AWS and containers, for example. It's quite complicated. AWS is very low level, so usually you have to create a lot of nitty-gritty resources and wire them together to make something simple. So Pulumi comes with a library called Crosswalk, which has a bunch of high-level components that simplify the task of like everyday provisioning containers or lambdas or whatnot or Kubernetes clusters. So one example, let's say I want to deploy a very simple infrastructure, a load balancer, and then 2 Nginx servers or containers that are behind that load balancer. So my diagram looks very simple, but the actual amount of AWS resources that you have to deploy for this is like 20 or 30 resources. But with AWS X Crosswalk Pulumi program, you can still use higher level components to define programs, and then your programs will have the same shape as the diagram I showed before. So you can immediately go from this to this. You write 1 line of code or 2 lines of code for a load balancer, and then you say, I want a new Fargate service with desired count 2 and this container, please. And you wire them together by passing a listener to port mappings. And that's all you need to do to define the infrastructure for this basic use case. But when you run it, you will see all the resources that have to be created, security groups, subnets, services, policies, and so on and so forth. You will still see them, but you don't have to laboriously define them again and again every time you need a new Fargate service. So that's the productivity boost that you can get by using general purpose programming languages and components. You can also create those components yourself. So let's say you work on an e-commerce website, something like Amazon or Amazon competitor or other, and you're working microservices teams and you deploy to Azure. And your challenge is that your customers are all over the globe. So somebody is in the US, somebody in Europe, somebody in Asia, and you want to deploy your infrastructure close to the end user so that the latency is minimal and so on and so forth. So for storage, let's say you can use Cosmos DB, which is geo-replicated database with multiple regions. But if I want to deploy my serverless functions, those functions are only deployed to one region. So if I want to be close to my customers, I have to deploy n copies of that function app close to every target region, 1 in Europe, 1 in US, 1 in Asia, for example. And then I have to wire them with the proper Cosmos DB replica and also put a front-end load balancer, say traffic manager, that would wire the user to the nearest location to the nearest function app. So you can see easily how I get like 20 resources out of just this geo distribution scenario. And maybe this is the setup that my team uses, but maybe a different team working, say, on a shopping cart, they have the same challenges of distributed people all over the world, and they have to deploy to multiple regions. But they don't use serverless functions. They use container instances, for example. So their infrastructure is similar, but different in some important ways. They have to deploy container instances and container registry, but all the rest of the wiring on the front end, on the back end, is still the same. Maybe the third team working on pricing engine, they still use some old Java application they can only run in VM scale set, so they have to deploy load balancers, public IPs, VNets, subnets, all the security groups and so on, and do it in every region where they deploy and copy it n times again and again and do the same wiring that all the other teams did. So we could sit down, three of those teams, and say, okay, we'll create a component that will abstract away or sort of make reusable all the wiring that they need for multiple regions, but it will still allow us to customize our pluggable application layer. I would put Azure functions there, you would put container instances there, and he would put virtual machines there. And once we create this component, we call it, say, Cosmos app. then the usage of that component is quite straightforward, and that's an example. So I create a new resource called function app, or Cosmos app, and then I pass a list of locations where I want this to be deployed. In this case, 3 locations: West Europe, West East, and Southeast Asia. And then that component will go ahead and call my infrastructure 3 times. We'll create Cosmos DB, we'll create front-end load balancer, and then when it needs to provision a compute layer, it will call my callback factory. And in this factory, I just need to provision my custom resources for one region. It will be called 3 times in this example. 3 times I'll create an archive function app, but code-wise, it's very simple. I put my code here inside the callback, and then I return back its URL or its ID from the callback to the component. The component does all the wiring. We can package this to our private NPM registry, may apply semantic versioning to it, distribute it to our multiple teams and so on. So we can apply the best practices of software development to our infrastructure code and reduce a lot of duplication across the teams. Final example I want to give is related to Kubernetes. So a lot of people do Kubernetes these days, and mostly they deploy to managed clusters in different clouds. So the complication of Kubernetes deployments is that there are multiple layers to manage there. First is infrastructure like networking and storage, identity layers in the cloud. Then there is that managed Kubernetes cluster, EKS, AKS, GKE. And then we probably also use some managed services from the cloud like Cosmos DB and start deploying multiple applications to that same cluster. And the good news is that you can apply the same approach that I described before to all of these layers in your program. So you can manage all of these layers from one program or other, from multiple programs talking to each other, because they're probably developed by different people at different time. So we even have a guide to how to apply this to Kubernetes deployments called Coursework for Kubernetes. The idea is that you use the same approach, the same TypeScript or Python or whatnot on all layers to provision all of them. And one layer above depends on all the layers below. So cluster provision will look a lot like what I showed before. And for application, we actually have a separate library called Kubernetes X, where you sort of write the resources that you normally define in your YAML files, but now you can write them in TypeScript with all the IntelliSense and IDE support. And it becomes very concise, because this is an example. You can create like pod build definitions and deployments in just a couple lines of code, and then wire them together. And in the output, you can apply these definitions with Pulumi CLI, or you can also dump them to YAML files and use your normal tooling to deploy those. So also the idea of creating components applies to Kubernetes as well. A final remark that I want to make is that you can also transition quality control practices from software development world and apply them to infrastructure. So one concern that I hear a lot from ops people is that, hey, if we give our developers full power of programming languages to define cloud infrastructure, they're going to do horrible things. They write horrible code, they create too much resources, or they avoid all the rules. Well, I don't agree with this. First, because, well, you can do horrible things with YAML as well, but also because in order to control what your developers do, there are ways to enforce this in the cloud, like policies and so on. You have to apply these ways regardless of the tools that you use. But if you use general purpose programming languages, then you can also start writing better automated tests. You can even do things like unit testing from development world. So without deploying anything, you write rules about the code. Like in this example, you say, I don't want to expose SSH port for my infrastructure, and I don't have to deploy this anywhere. You just, when you develop the program, you just write this test once. You commit it to your CI/CD pipeline, let's say, and every time somebody changes the code, it will check if your code did not expose SSH port to internet, and would fail the build if it did. So you can apply control and some practices, best practices on the level of unit testing, but you can also do integration tests and unit tests much easier with general purpose programming languages. One step forward is something we call policy as code, where you can define sort of the same unit tests, but then you define them, you put them into packs, like independent things from your actual code. You deploy them to your company-wide, let's say, and then these rules will be evaluated every time somebody in your company runs the deployment to AWS in this case. So it's not tied together to the code, to the actual code that you write, but you do this once, like you are, say you are a security officer, you do it once, you write those policies, you deploy them once, and every time somebody in your company tries to deploy bad things to production, it will fail at that deployment even before it tries on AWS, because the rule is violated, let's say because SSH port is exposed or public internet is exposed. So that's the power of general purpose programming language that you get here. So wrapping up real quick conclusions, and then I can jump to the questions if we have any. So if you are working on cloud applications, any sort of cloud, any sort of tools, my first advice is please use some sort of infrastructure as code. Pick your favorite language if you're happy with CloudFormation or Terraform. Pick those, but I strongly advise to use Pulumi or things that rely on general purpose programming languages. But any tool is better than just clicking in the portal and or ad hoc scripts that you create. I strongly believe that general purpose code or real code will help you maintain your infrastructure in better shape. It's developer friendly, so operators and developers can work together to define better infrastructure and to teach developers to work on applications on infrastructure level. Logic like conditionals and loops and classes and components are built in right there. You don't have to invent bicycle again. You just reuse the same constructs that you get from the language. And the biggest advantage for me is that you can create abstractions and reuse abstractions to create components, sort of to make the common tasks that are repeated again and again less laborious and more error resistant and more reliable. You can define some abstraction once, distribute them on your team or general open source community, and everyone benefits from that. So in my opinion, we sort of go from infrastructure as code, where you define nitty-gritty, low-level details of all the resources in AWS or Azure, to more of architecture as code, where your final code looks a lot like your diagrams that you draw on the board. Back to the Fargate example, where we had a load balancer and two Fargate instances on the diagram, and the code had exactly the same shape. So it's easy to go from diagram to code, from architecture to code. And that's the idea of more productive infrastructure provision in the cloud. So I'm done with this. If you want to see my slides after the session or some useful links to other resources like Slack, or where you can ask questions, please make a screenshot of this slide and go to the first URL. You will find slides there. You can still ask questions on slide. I don't see any questions at the moment, but if you have one, you can fire them up right now. Or later you can contact me on Twitter at Maikhail Shilkov, or my email is also on the slide here. Right after I finish this presentation, I will go to this Zoom call at the bottom. So if you want to chat with me in voice and like have a conversation instead of just Slido, you can also join that call. It's open to everyone, so I'll hang there for like half an hour after the call. So with this, I'm done. Thanks for attending the conference. I wish you a very good day and a very pleasant virtual experience at this conference. I don't see any questions, so I think I'll wrap up here, and we'll take questions on Twitter or Zoom call afterwards. Thank you.